This is question 36 from the GATE 2018 EE paper, where we are given the following sequential circuit and are asked to find out which of the following statements is true for it. Underneath the question, you will find the title of the NPTEL course or video relevant to the topic.
So let's look at the solution to this problem. This is a sequential circuit. So the first step would be to label the state variables, which are the outputs of the flip-flops. So I'll call this Q2, I'll call this Q1, and I'll call this Q0. With the state variables labeled, let's look at the next state equations. So Q2 plus is whatever Q2 will be after the clock hits, right? I'm assuming this is a positive edge triggered flip-flop. So after the clock hits, Q2 plus will take on the value of whatever D was when the clock hit, and D will be what the current value of Q1, current value of Q0 NANDed is. So it's Q1, Q0 the whole bar. And this is just because of this connection, this is just a shift register. These are just two shift registers. So Q1 plus will be Q2 and Q0 plus will be Q1, right? So we now have the next state equations for the state variables, right? With that we can form the state table of the counter. So the idea is that to populate the 8 states that the current state can be in and see what the next state is for each state. Let's take for example Q2, Q1, Q0 being 0, 1, 0. That is this row. So we have to find Q2 plus, Q1 plus and Q0 plus. That is, we have to find this. So Q2 plus is this and this going through a NAND gate. As you know, the NAND gate output for those inputs are 1, right? And since it's a shift register, this value will just come here as 0, 1. It just shifts 1 to the right. So the next state is 101 as obtained over here, and like this we can obtain the next states for all of the 8 possible values that Q2, Q1, Q0 can go to. With this out of the way, you can see that if the starting state for example is 100, the next state is 110, which goes to 111, which goes to 011, which goes to 001, and finally comes back to 110, right? So this is a periodic state sequence. So if for example the flip-flops were to ever get into one of these states, any one of these states, for the remaining clock cycles it would just keep cycling between these states, because this is a periodic state sequence. That is, you start and end in the same states, right? And these, you notice that there are 5 states here, but there are totally 8 states that Q2, Q1, Q0 can be in. So the remaining 3 states are here, right? And what you can see is that if you were to, let's say, start at 000, you would go to 100, which is the first state in the periodic state sequence. And if you were to start at 010, you would go to 101 and then eventually come to 110, which is the second state in the periodic state sequence. So even if you start in one of these non-included states, that is states that are not there in the periodic state sequence, maximum you can be there only for 2 clock cycles, after which you will land up in a state that's in the periodic sequence, right? So ending up in one of these states is only a transient phenomenon. In the steady state, it will just go through these states. So let's look at what the steady state periodic sequence is. So as shown in that table, it is as so 100, 110, 111, 011, 001 and 100, right? This is one cycle, right? And this is the start of the next cycle. So one periodic cycle lasts for 1, 2, 3, 4, 5. It lasts for 5 states. That is 5 cycles, 5 periods of Fn, right? Fn is the clock input to the 3 flip-flops. So this has a periodic sequence which lasts for 5 periods of Fn, that is for 5 clock activations. And since Q0 is what Fout is, you can simply take, this is Q2, Q1, Q0, so the third bit is Q0. You can simply copy Q0 over to find out what the periodic sequence is in Q0. You can see that Q0 also has a cycle, right? This is one cycle and this is the start of the next cycle, and the length is 5 cycles, 5 periods of Fn, 5 periods of Fn. So the idea is that this is a frequency divider and it divides by 5. It takes an input clock frequency and gives an output clock frequency of Fn divided by 5, because the time period at the output is multiplied by 5. So the frequency, which is the 1 by the time period, is divided by 5. So this can be used for dividing the input frequency by 5. And of course, if B is true, A and C, which are the same answer but with different numbers for the divide by factor, are false. And D is also false because it's not that the internal cycles are disjoint. That is, it's not the case that there are 2 separate cycles of states which are disjoint from each other. It's actually that there is only one cycle of states and the remaining 3 states will eventually join. Actually, so the remaining, if you start at 0, 0, 0, you'll land at 1, 0, 0, and that will go on to come as a periodic cycle, right? And if you start at the other 2, which is 0, 1, 0, 0, 0, 1, 0 and 1, 0, 1, you will just have 0, 1, 0 going to 1, 0, 1, going to a state in the periodic cycle here. So there is only one cycle internally, not that there are multiple disjoint internal cycles. So the correct answer to this question is B.